Okay, let's unpack this. Think about some of your favorite things made from, natural fabrics, that super soft cotton t-shirt you love, maybe those crisp linen sheets.
Yeah, we love them. They're comfortable, they breathe well, they just feel great against the skin.
Exactly. But they do have natural limits, right? They soak up water like crazy, for one.
Mm-hmm. And they can catch fire pretty easily, too.
Right. And these natural traits kind of restrict where we can safely and effectively use them.
Yeah.
Think about certain furniture, protective gear, even clothing that needs to handle the elements.
Absolutely. And that's precisely the challenge that the source material you shared is tackling head on. It's quite a fascinating research paper.
Yeah, it's from the J Innovative Nat Sign, published just this year.
That's the word.
So our mission for this deep dive is really to slice through let's say, the dense technical language in this paper.
Yeah, pull out the key stuff.
We want to pull out the absolute most important insights, the core findings about how scientists are developing these new, sustainable ways to make cotton and linen, well, not just more water repellent, but also flame resistant.
Think of this as your shortcut, Your fast track to understanding the cutting-edge science in this specific area of textile research. We'll highlight the surprising discoveries and the potential without getting totally bogged down in every single experimental detail.
Okay, so to really appreciate what they're trying to achieve here, it probably helps to understand the sheer scale of the industry we're talking about. The paper gives some context, right?
It does. The global textile fabrics market is, well, it's enormous. It was valued at $920 billion back in 2018.
Wow.
And projected to hit $942.8 billion this year, 2024. That's a steady 5% growth rate. It's a massive, vital industry.
And natural fibers are right there at the heart of it all. Cotton's a huge player, something like 38% of the total fiber market last year.
Mm-hmm. And linen, too, known for its strength. Very important natural fibers.
But, like we said, despite being so popular and having great qualities, comfort, breathability, their inherent properties are a problem.
Right. Being hydrophilic, that's the water-loving part. They absorb water readily, and their flammability. These really limit their application.
Especially where safety is critical. Homes, cars, offices, maybe specialized protective clothing.
Exactly, those areas.
Now, obviously, treatments exist already.
Right.
Ways to add water repellency or make fabrics less flammable.
Sure, those methods are out there. But the paper brings up a really crucial point about them.
Which is?
It highlights that a major concern with many of those sort of traditional textile treatments is their environmental footprint. And potentially their health implications, too. Many rely on pretty harsh chemicals or processes that use a lot of energy.
Okay, so that's the problem of the old ways. And this is where the study you shared offers something different.
Precisely. This research digs into enhancing these properties using coatings that are, get this, both UV curable and derived from bio-based renewable materials.
Bio-based and UV curable.
Yeah, and this approach aligns perfectly with that growing global push for sustainability we're seeing everywhere, including in the textile world.
Okay, let's zero in on that innovative approach then. These UV curable coatings. What exactly are they doing? What does that mean?
So the core technology revolves around using photocurable coatings. Think of them as special liquid coatings that harden or cure almost instantly when you expose them to specific wavelengths of UV light.
Ah, UV light. Okay. What makes using UV light for curing so, well, attractive as a method?
Well, the paper points out several key advantages. First, it's incredibly rapid. We're talking seconds or minutes for the curing process.
Wow, fast.
Very fast. It's also a low-temperature process, which is a big deal because it saves a lot of energy compared to traditional heat curing.
Okay, energy savings, that's huge.
And crucially, it's often a solvent-free process, meaning no volatile organic compounds or VOCs being released.
Right, no nasty fumes. So energy savings, less environmental impact, safer. Sounds like a pretty significant win already.
It really is. The paper presents it as, a state-of-the-art, versatile, and potentially quite cost-effective option for finishing textiles, especially compared to some older methods.
And then you layer on the bio-based element. What's the specific advantage there? Why go bio-based?
Well, using materials derived from renewable resources, think plant-based compounds obviously reduces our reliance on fossil fuels. That's a big plus.
Right.
It also typically results in very low, sometimes even zero, VOC emissions. So that's better for the environment and for the health of workers handling the materials and eventually the consumers.
Makes sense.
And sometimes these bio-based materials can even offer unique performance benefits, like maybe better adhesion to the fabric or improved barrier properties.
So is this combination bio-based materials, specifically these acrylates, cured with UV light for textiles? Is this something researchers have been doing for a while?
Well, that's what's interesting. The paper actually notes that research specifically looking at using bio-based acrylates in photocurable textile coatings is still relatively new territory.
Oh, really?
Yeah. They mentioned, previous studies have touched on related areas using bio-based compounds in general or UV curing for other types of coatings. But research focusing on creating multifunctional coatings for textiles.
Like hitting both water repellency and flame retardancy at once.
Exactly. Doing that using these specific types of bio-based acrylates and UV curing. Well, the paper suggests there are still significant research gaps there. This study is trying to fill one of those key gaps.
Okay, so they designed experiments to see if they could actually bridge that gap.
Yeah.
Let's look at the two main coating strategies they explored in this paper. What did they actually do?
Right. First, they needed the fabrics, obviously. They used two very common natural fabrics, 100% linen described as light yellow, closely woven, about 122 grams per square meter.
Okay, standard lemon.
And 100% cotton. This one was gray, had a pile weave, and was a bit heavier at 179 grams per square meter, just standard stuff you could buy.
Got it. Okay, tell us about the first coating recipe they tried out.
So this first approach involved combining a specific bio-based compound. It's called methacrylated phenolic lipid. Thankfully, they shortened it to CSM in the paper.
CSM.
And this CSM was derived from cardinal. Cardinal is a natural liquid extracted from cashew nutshells.
Oh, cashews. Okay, so definitely a renewable resource.
Exactly, a great example. They mixed the CSM with different ratios of simpler chemical building blocks called N-alkyl myricylate monomers. Specifically, ones with 12 and 18 carbon atoms in their chain, often just called C12 and C18.
C12 and C18 monomers mixed with the cashew stuff.
Right. This liquid mixture was then applied to the fabrics and then, zap, cured under UV light. The goal here was to use these components together to create a surface layer that would hopefully be both hydrophobic, water-repelling, and also contribute a bit to flame resistance.
All right, so that's recipe one. The CSM from cashews plus those C12, C18 molecules all mixed and cured. What was the second strategy they tested?
The second approach was a bit different. It was a two-step process. And this one was designed specifically to really boost the flame retardancy using a known effective compound.
Okay, a more targeted approach for fire resistance.
Exactly. First, they applied a very thin layer of a chemical called 3-aminopropyltriethoxysilane. Let's just call it APTs.
APTs, got it.
This APTs acts like a primer. It helps prepare the fabric surface, often improving how one to the next layer sticks.
Like priming a wall before painting.
Kind of like that, yeah. Then on top of that APTs layer, they applied another substance called acrylated DOPO. Now, DPT stands for 9010 dihydro-9-oxy-10 phosphophonanthine-10 oxide.
Whoa, that's a bit of a mouthful.
It is, but DPO is a well-established flame retardant molecule. It contains phosphorus, which is key to its function. So this two-layer system, APTs then DOPO, was then also cured using UV light.
Okay, so one approach mixed things together hoping for combined effects, and the second layered a known flame retardant on top of a primer. Makes sense. How did they actually measure if these coatings worked? What tests did they run?
They used pretty standard tests for the properties they were aiming for. For water repellency, they used the water contact angle test, or WCA.
WCA, okay.
This basically measures the angle a drop of water makes when it sits on the fabric surface. A higher angle means the water beads up more, which indicates better water repellency. Think water beating on a waxed car.
Right. A high angle is good for staying dry and for flame retardancy.
For that, they used the limiting oxygen index test, or LOI. This test figures out the minimum percentage of oxygen needed in the surrounding air for the fabric to actually keep burning after it's been ignited.
LOI. And how does that relate to normal air?
Well, normal air is about 20.9% oxygen, so if a fabric has an LOI higher than, say, 21%, it means it won't keep burning in normal air once the ignition source is removed. A higher LOI value means the fabric is harder to burn.
Okay, higher LOI, better flame resistance.
Got it.
All right, let's get to the core findings then. What did these tests actually reveal about the coated fabrics? What were the key nuggets, the main takeaways from the results?
Okay, let's look at the water contact angle, a WCA, first. The uncoated linen fabric, the baseline, had a WCA of just 38 degrees.
38 degrees, so water just soaks right in, basically.
Pretty much instantly. Cotton was similar, also had a very low baseline WCA, very hydrophilic, like the paper said.
Right, water-loving.
Exactly. But with that first coating strategy, the one using the CSM from cashews and those alkyl acrylates, they saw a really significant transformation. Adding those alkyl acrylates seriously boosted the water repellency.
How much of a boost?
Well, one key insight here was that the length of the carbon chain in those alkyl acrylates really mattered.
Ah, the C12 versus C18 thing?
Precisely. When they added 17.5% of the C18 monomer, that's the one with the longer 18 carbon chain, they achieved a WCA of 98.5 degrees on the linen fabric.
Wow, 98.5 degrees. That sounds really high. What does that number actually tell us in practical terms?
Well, any WCA over 90 degrees means the surface is considered hydrophobic or water repellent, so hitting 98.5 degrees. That means water drops aren't spreading out and soaking in at all. They're forming these tight little beads and just rolling right off the surface.
That's a huge difference from 38 degrees.
Yeah.
A major step towards making these fabrics genuinely water-shedding.
Absolutely, a dramatic shift.
And did the paper explain why that longer carbon chain, the C18, works so much better?
Yes, it did. They point out that those longer alkyl chains, like C18, are inherently hydrophobic, just at a molecular level they don't like water.
Okay.
So when they become part of the cured coating on the fabric surface, they create a kind of barrier. It's almost like they physically prevent water molecules from getting close enough to the underlying fabric fibers to interact with them.
Like a microscopic shield or something.
You could think of it like that, or like
Yeah.
a dense forest of water-repelling chains blocking the path. They also noted something interesting, a difference between the two fabrics.
Oh, what's that?
The coated linen consistently showed higher WCA values than the coated cotton, even when treated with the exact same coating mixture.
Huh. Why would linen behave differently than cotton that way?
The paper suggests it probably comes down to the inherent differences in the fiber structure and the surface of the two fabrics. Linen fibers tend to have a rougher texture, and they also have a higher natural content of something called lignin.
Lignin, okay.
These features, the roughness and lignin, might help trap tiny pockets of air on the surface when the coating is applied. And trapped air is actually very effective at repelling water. It contributes to that beading effect.
Ah, like how some insects can walk on water because of trapped air.
Sort of analogous, yeah. They also speculated that linen's coarser structure might provide better mechanical anchoring, or maybe just better adhesion for the coating compared to cotton's smoother surface. This could lead to a more stable, more effective hydrophobic layer on linen.
Interesting. Okay, so that covers the water repellency side pretty well. What about the flame retardancy results? How did the LOI tests turn out?
All right, the LOI. So for the baseline, the uncoated fabrics, linen had an LOI of 18.0%, and cotton was very close at 18.4%.
Both well below that 20.9% oxygen level in normal air.
Exactly. Meaning they can easily ignite and keep burning in normal conditions. They definitely require less oxygen than is typically available to sustain combustion.
Okay, so how did the coatings change that? Let's start with the first strategy, the CSM and alkyl acrylates one.
Okay, with that first coating strategy, they saw only a modest improvement in LOI. It bumps up to around 19-20% depending on the exact mixture they used. For example, one specific mix got the linen up to 20.2%.
20.2%. Better, but still below or right around the level of oxygen in the air. Not a huge jump towards being really flame resistant.
Not really, no. So that formulation, while great for water repellency, didn't do all that much for fire resistance.
Okay, so that first strategy was great for water, less so for fire. What about the second strategy? The one with the APT's primer and the DOPO top coat?
Now that one showed a much, much more significant enhancement in flame retardancy. The LOI for the treated linen jumped substantially, all the way up to 25.9%.
25.9, that's a big leap.
It is. And for cotton, it jumped to 24.4%, also a very significant increase.
Wow, okay. What does that jump to 25.9 or 24.4 actually mean in terms of how resistant the fabric is to catching fire?
Well, these higher LOI values are comfortably above the oxygen level in normal air, around 20.9%. This means the treated fabrics now require a significantly higher concentration of oxygen than is typically available in the atmosphere just to keep burning.
So in regular air, they'd be much harder to ignite, and they'd likely self-extinguish if the flame source was removed.
That's the implication, yes. It makes them far more resistant to igniting and sustaining combustion under normal conditions. And the paper confirms why the DOPO molecule is so effective.
How does the DOPO work?
It works in a couple of ways. It's known to interrupt the chemical chain reactions that happen during burning, effectively snuffing out the flame in the gas phase. And importantly, it also helps the fabric form a protective char layer when it's exposed to heat.
A char layer, like it burns to a crisp but doesn't really burst into flames?
Exactly. That char acts as a physical barrier, insulating the underlying fabric from the heat and limiting the release of flammable gases that fuel the fire.
Okay, that makes sense. So pulling it together, the studies successfully showed they could enhance both properties, water repellency and flame retardancy, just using different approaches or recipes for these bio-based UV-cured coatings.
Precisely. They demonstrated it's definitely possible to significantly boost both water repellency and flame retardancy in these very common natural fabrics using these novel coating types.
And it seems like each coating recipe really had its own particular strength, right?
Yeah. Absolutely. The first method, the one combining the CSM from cashews and the alkyl acrylates, that was particularly effective for creating a highly water-repellent surface. It achieved that impressive 98.5 degree WCA on linen.
Great for waterproofing.
Yep. And the second method, the two-step process using the DOPO GMA system, that acrylated DOPO, that was a clear winner for adding flame retardancy. It pushed those LOI values well into the genuinely fire-resistant range for normal air conditions.
So how did these results, and maybe just as importantly, the methods they used, stack up against other ways people have tried to treat fabrics in the past? Did the paper comment on that?
Yes, they did compare their approach, at least conceptually, to some existing methods mentioned in other research papers. One key insight they highlighted is that while similar WCA or LOI values have been achieved before in other studies using different techniques, their UV curing method seems to offer some real efficiency advantages. For example, that CSM-based hydrophobic coating used a relatively simple one-step application followed by the quick UV curing. They suggest this could be simpler than some other multi-step techniques like layer-by-layer assembly, which is sometimes used for surface modifications in which they referenced.
Fewer steps, faster process, potentially.
Right. And the DPO GMA system, the flame retardant one, also potentially offered a faster process compared to some other flame retardant treatments. Plus, in their specific tests, it resulted in good char formation and, interestingly, reduced glow time.
Glow time? What's that?
That's the sort of smoldering or afterglow embers that can sometimes persist even after the main flame has gone out. Reducing that is also important for fire safety.
Ah, I see. Okay, so potentially simpler, faster, and effective results. That sounds really promising, especially the efficiency aspect. But, this is research. There's always more work needed before something like this ends up on a t-shirt or sofa, right?
Oh, absolutely. While the findings are definitely very encouraging and they clearly demonstrate the feasibility of the approach, the paper is quite clear that more research and development are needed before these coatings could be ready for widespread, practical commercial application.
What specific areas did they flag as needing more work? What are the next steps?
Well, one key area they mentioned is really optimizing the UV curing process itself.
Getting zapped just right.
Exactly. They need to systematically investigate things like the precise exposure time to the UV light, the intensity or power of the light source, and also the concentration of the photoinitiator.
Photo what?
Photoinitiator. That's the special substance mixed into the coating that actually absorbs the UV light and kicks off the chemical reaction that hardens everything. Fine-tuning all those parameters is absolutely essential to get the absolute best performance out of the final coating.
Okay, makes sense. Got to dial in the recipe perfectly. What else?
They also pointed out a really critical gap that, frankly, they didn't fully address in this particular study. That's exploring whether different acrylate compounds, maybe some of the ones they use, maybe others, could be combined synergistically.
Synergistically, meaning working together.
Yeah, working together in a single coating formulation to achieve both high water repellency and high flame retardancy simultaneously from just one treatment.
Ah, the holy grail. One coating that does both really well.
Kinda, yeah. They note that current research often tends to focus on optimizing just one property at a time. So developing a truly multifunctional single coating using these bio-based UV systems, that's a key future challenge. And of course, long-term durability is crucial.
Right. How well does it hold up?
Exactly. How do these coatings perform after multiple washes? Or being rubbed and abraded, or just being exposed to sunlight and different environmental conditions over time? That needs really thorough testing.
Yeah, you don't want it washing off after the first cycle. And what about actually making this stuff? Taking it from a small lab experiment to, a big factory process?
Scalability, yep, that's definitely mentioned as a potential challenge too. Adapting UV curing methods for continuous textile finishing, imagine huge rolls of fabric moving through a production line, can be tricky.
I can imagine.
Yeah, particularly ensuring you get uniform application of the coating and consistent, even curing across really wide areas of fabric. That's something future work will absolutely need to examine. The industrial feasibility and the nuts and bolts of scaling up these specific coating formulations and processes.
Okay. So we started this deep dive thinking about those really familiar limitations of our favorite natural fabrics, cotton and linen, how easily they get wet, how quickly they can burn. And this look into the research paper really shows some remarkable progress being made in overcoming those challenges. And, importantly, doing it in ways that seem innovative, sustainable, using bio-based materials, and efficient, thanks to that UV curing.
Absolutely. By developing and applying these different bio-based acrylic resin formulations, whether the CSM mix or the DOPO system, and then curing them rapidly with UV light, the scientists achieved some really impressive results. They successfully created versions of linen and cotton that are both highly water repellent.
Making water beat up and roll right off.
Right. And also significantly more resistant to burning in normal air conditions.
It feels like this study really opens up some exciting possibilities for the future of these natural textiles that we use every day.
It really does. If these sustainable, efficient coating methods can be perfected, if they can figure out that multifunctional coating and if they can be scaled up effectively, just imagine how the properties and the potential uses of the natural fabric surrounding us could fundamentally change.
Yeah, it really makes you think.
Which brings us to a final thought for you, our listener, to consider. If cotton and linen fabrics you know so well were suddenly reliably water repellent and fire resistant thanks to sustainable tech like this, what new applications or products could you envision for them? Where might you start seeing them used? Maybe in your own home, your clothing, or even further afield.